Very much. I'm Dylewsky. I'm a postdoc here at Waterloo. And I'm going to be talking about work that I've been doing recently on deep learning for early warning signals of tipping points in climate systems, and specifically with regard to phase transitions, which I'll talk about. So this is all work from a recent paper that we published. So I just wanted to give a quick acknowledgement to my co-authors and our funders and so on. So basically, the foundation, the background for this work is the idea that, it's certainly in climate context, becoming increasingly apparent that there's the possibility of these abrupt tipping events in a variety of climate systems, where basically, regardless of the specific mechanism involved, but there's the possibility that a system will sort of reach a point of suddenly some feedback will occur that will cause it to abruptly change from one equilibrium state to another. And so there are a lot of examples of this you can think of, maybe you've heard about with respect to like Arctic permafrost, that there's carbon sequestered in the Arctic permafrost. Obviously, as the Earth melts, that will start to be released into the atmosphere. Carbon being released into the atmosphere exacerbates and increases the warming of the Earth. And so there's the risk that if that rate of release ever got high enough, then you would get to a point of feedback where suddenly that would be kind of a runaway. We're not there yet, but that's sort of an intuitive example of the type of phenomenon I'm talking about here. And so in a climate context, that's obviously important because any kind of sudden and abrupt transition could be extremely dangerous and damaging in a lot of ways. And also it's difficult because the methods that we have for modeling climate systems, these are already very complex systems in a lot of ways. It's obviously not easy to model, but it's particularly difficult to model when it comes to these abrupt tipping events, because it's hard to build a model when you've only kind of seen one side of that tipping. Like we don't have the other side of the regime to tune our models with. So that kind of is the motivation for this space that we've been working in, which is this idea of looking for early warning signals associated with these tipping events. So I wanted to give a little mathematical background here. Basically, the simplest kind of mathematical description for this type of phenomenon that I'm talking about comes from the theory of bifurcation theory. And so this little cartoon that I have on the right here kind of gives a sense of the type of phenomenon that I'm talking about, where the ball there represents our system sitting in some kind of local minimum of potential, which is just whatever equilibrium the system happens to be living in. And a bifurcation will occur when that equilibrium point becomes unstable as a result of some kind of external forcing on the system. And so you can see sort of the before and after of the two frames of this panel here, that you can imagine if the system is sitting in a sort of a steep wall of local equilibrium, as we see on top, that any small perturbation out of that equilibrium, it would start to return to that local minimum. And so we can observe, in any given complex climate system, we can kind of think of it as constantly being stochastically perturbed in small ways from whatever environmental coupling it has. And so we can observe it returning to equilibrium. The thing that we're looking for as an early warning signal for this type of tipping events is that before that equilibrium actually becomes unstable and the system tips and runs off to a new equilibrium, there will be this time frame under which that potential well that it sits in becomes increasingly shallow. And so you'll see small perturbations away from that minimum. It takes longer and longer to recover. And so that's kind of that's what we're looking for as a warning of these things coming on. And what's particularly useful about that is that that's extremely generic across a very broad class of systems. Yes. So.
Question. We'll have to do that at the end.
Okay. But is there anything quick that you can clarify, or?
Well.
Okay.
It's not technical. Yeah.
Okay. So essentially, the idea is that we're looking for methods for looking for these dynamical features that would precede the bifurcation. And so that's kind of the framework in which we're working. And that's potentially a very valuable alternative to traditional climate modeling methods, which, as I said, can sort of struggle when it comes to these tipping events. So there has been a fair amount of work on this subject in the last decade or so. And there are a bunch of statistical methods that one can use to look for these sort of critical phenomena that precede a bifurcation event. So things like looking for an increase in the variance of your time series or an increase in the lag one autocorrelation, which are just basically statistics that are associated with that slowing phenomenon that I described. But more recently, there's been the question of, can deep learning methods or machine learning methods more broadly do better than these sort of traditional statistical approaches? And that's motivated largely by the fact that deep learning has shown a lot of promise in other arenas doing time series classification. So it seems like potentially a powerful tool for this subject. And these results here I'm showing are from this paper by Tom Burry et al. In 2021, where basically they did exactly that, and showed that for a collection of sort of canonical codimensional bifurcations, not only was their model able to predict these things before they happened, so you can see in these plots that I show the probability that the model outputs as over time, as it sees more and more of the time series, it'll start to pick up on the oncoming bifurcation considerably before the actual dotted line indicating when that transition takes place. Not only that, but it's actually being able to distinguish between some of these different subspecies of bifurcation, which gives us some additional insight potentially into not only that there's some kind of tipping point being approached, but what the dynamics on the other side of that tip might look like. And the key insight of this work was that you can take advantage of the kind of universal property of these early warning critical behavior phenomena, that if you want to test your model on some climate application, whatever it might be, but you don't have plentiful data of that particular system with ground truth labeling on which to train your neural network, then that's an issue. But what you can do is instead build up a large simulation data set of simple examples just based on some, whatever simple version of a bifurcation you want to cook up. And then the hope is at least that a neural network model trained on that data will learn these universal characteristics. And then when you transfer it over to the test subject of interest, that it'll actually still be, even though it hasn't seen that particular subject in its training, it'll still be able to successfully characterize an oncoming bifurcation event. And in fact, this paper, the Burry et al. Paper, confirmed that seems to be the case, that it does a pretty good job even on systems that are tested at a sample. So the work that I'm presenting here from my recent paper is basically trying to extend this work to a broader class of critical transitions than is sort of contained in a simple set of bifurcations. And in particular, we're interested in an alternative mathematical description of these types of events, which is from statistical physics, the theory of phase transitions. Now, between phase transitions and bifurcations, there is sort of a spiritual relationship, and there are connections between the two. And in fact, in some cases, a phase transition, you can write a simplified approximation of it, which just sort of reduces to the form of a bifurcation. But it's kind of a broader and a little bit less well-behaved, perhaps, collection of potential critical transitions. And in particular, these are transitions that occur in high-dimensional systems, often spatially resolved systems. So, this example I've shown in the animation on the right is on a spatial lattice. And you get a transition from one sort of, in this case, what we're seeing is the easing model, which is a canonical example of a phase transition that's used in statistical physics. But we're watching it undergo a transition from a disordered phase in which the white and black are all kind of mixed up together to an ordered phase where they start to kind of collapse into separate domains and sort of develop order in that sense. And so these are the examples from which we want to build up a training data set to then train a deep learning model and test on real world examples. And the reason that this is kind of well motivated, especially in a climate context, well, there are a few reasons, but in particular, number one, climate systems are often the data that we have available is, remote sensing satellite data, where we have some spatial and temporal resolution of the data. and that we can look for, it's sort of theoretically established that these critical transitions, not only do you see sort of a slowing in time as you approach the transition, but there are certain spatial correlations that are also expected to emerge. And so other models haven't really looked for that. We wanted to explicitly look for that, because if we have that spatial information on a system we're interested in, we want to make use of it. And then there are some examples in sort of toy climate models of how it's been proposed that phase transitions are taking place within climate subsystems. So the examples that I give here are, for example, in vegetation systems, sometimes you'll see if a system is going from a vegetated state to, say, an arid desert state, it will undergo what can be described as a phase transition. Or likewise in sea ice systems, it's been proposed that the porosity of sea ice and the related properties of how liquid is able to transport through it can undergo a percolation phase transition. So the methodology is very similar to what I described before, where we're training a model on simple synthetic data with the idea that it's going to learn certain universal characteristics and then be applied to more realistic data. So I won't go too much into the details of how it was structured and all, but one key component of how we decided to organize this data and organize our models was that we have separate models trained on only temporal statistics associated with the data, only spatial statistics, and then some that are trained on a combination of both. And that just kind of allows us to I'll show you some results for those different subcategories of the models. And we're looking at training data just drawn from that Ising lattice model that I showed the little animation of earlier, which is just kind of a canonical phase transition model. And we have two training data sets containing first versus second order phase transitions, which if you don't know what that means, I won't get into it. But so that's kind of the task that these models are trying to do, is to classify which of those runs are approaching a bifurcation, which ones are not. So these initial results I'm showing are for how the models perform, basically tested on withheld data that is, the same Ising model data that they were trained on, withheld runs from that, just how do they do classifying nodes. And so the top plots are just examples of what these transitions look like, the second on the left and the first order on the right. So the system approaching that vertical black bar indicating where the critical point occurs. And then on the bottom is the accuracy of the models in distinguishing critical versus non-critical runs, a certain number of time steps before that transition. So this is not climate data that I'm showing now. In a couple slides, I'll show then the same model applied to climate data. Sorry, yeah, I know a lot of people in the room are not math people, they're climate people, and therefore this might be a little bit sort of coming out of left field.
I'm actually working on ISIS.
Oh, perfect.
It's fine.
Yes, and so the results here, mainly the takeaway here is that we can see the model sort of getting up to a high accuracy level, even 100, 150 steps before that transition takes place. So that's a good news from the perspective of if we're looking for an early warning signal, we want to make sure that it's getting to that confidence level well in advance of the transition actually taking place. And there is, we could talk more about the relative performances of the spatial versus temporal models, but I'll leave that aside for now. So now, sort of taking this model a step further, we want to show that not only does it work well on the data that it was trained on, we want to show that it can actually be transferred over to data that it's never seen before, because that's kind of the whole point of the project here. So these are a couple sort of toy systems of climate resembling systems undergoing phase transitions. These are not, fully climate realistic systems. They're relatively simple toy models, but they at least have some resemblance. One of them is a coupled water vegetation system, and one of them is a percolation transition resembling what has been proposed in sea ice. And so then these results that I'm showing are ROC curves, basically plotting false positive rate of the model against true positive rate. And to interpret these, basically the larger the area under that curve, the better the model is doing. So the main takeaways here are that the models are doing reasonably well, which is encouraging given that these are both data sets that they never saw in training, they were never exposed to these. And so this suggests that they have in fact learned some features which are universal and transferable from one phase transition to another. And then the other main takeaway is that consistently we see the models that have only the access to those temporal features doing not as well as the ones that have access to the spatial features, which kind of indicates our decision to pursue this in the first place, because one of my main motivations was to say that if we're not taking into account that spatial information, we're losing out on some valuable information. And so then this is kind of a step up from those results to more realistic climate data. So this is testing on data from the CNIP5 data consortium of basically these are data on a lot of different climate domains pulled from these large global circulation models. And this test data set, we don't know anything about, like, it's hard to take a big complicated global circulation model and point to like this is for sure a bifurcation or a phase transition occurring in this subsystem. Instead, what we did was we pulled results that another group published of just a catalog of observed abrupt transitions in these simulations. So if you see one of these variables changing very abruptly in kind of a coherent way, then that suggests that there could be some kind of tipping going on. So it's a little bit woollier in the sense that we don't know that these positive label runs that we're testing on are actually dynamical phase transitions, but it's at least kind of a good enough test set that if we are able to consistently discriminate those from null other examples pulled from the same data sets, then that suggests that the model is doing reasonably well. And I've broken up our results here by different subdomains of those variables. So the colors here refer to, let's see, it's the blue is the atmospheric variables, the pink is the land cryosphere, the green is the land variables not in the cryosphere, and the yellow is the ocean cryosphere. So main upshot from this is obviously there's a fair amount of discrepancy in doing very well in some cases and not very well at all in other cases. You can think of a sort of perfect diagonal line of 50% of the square covered as being that would be the curve that you would get from just a random classifier with no knowledge of the system. So that's a failure, whereas on the left, the green curve would be a good success. So there's probably too much that I could say about why we're seeing what we're seeing here, but the main kind of takeaway that I would say I want to highlight is just that this kind of gives us a little bit of a sense of where these models might continue to be useful, in that sense that if we're doing well on this realistic simulation data, then we can maybe start applying to real climate data. Whereas in the domains where it's failing to do well, then we have to do some more exploration of why that is. It might have to do with sort of dynamics at different spatial or temporal scales that our system is just not sensitive to. So ongoing work.
Yeah, and if you could wrap up.
Okay, yeah, this is my last slide. And this is just a similar curve associated from data from the paleoclimate record. So this is now finally getting to not simulation data, but real data. This is purely a temporal data set, so we don't have the spatial curve, but just to show that even in that case, it still does reasonably well in classifying these observed events in the paleoclimate record. So with that, I will conclude, and I'll just show this plot on the last slide of this is kind of, an example of where we might eventually want to take this type of model if you can feed it, remote sensing data from real satellite data sets that are available. You can imagine taking a tool like this and generating kind of risk heat maps of where and when these transitions might be approaching. I don't think that we're quite there yet, but you can see kind of in this plot where how that might look as we continue to improve and robustify our model results. So with that, I will conclude.
All right, thank you.